Okay, let me put it on full screen. So good afternoon. I'm Yan Foucault from National Taiwan University, and I'm presenting this work for my student Cheng-Yin Lin, because Cheng-Yin passed away 2 weeks ago, and that's a big loss for all of us. Please give me a second. Cheng-Yin 老师来帮你报告。Okay, so the title of this presentation is Crop Identification for Agricultural Survey using a Vision Transformer. And so what is agricultural survey? It's to know what land is for what usage, say what crop you cultured in this land. And we can do it in several ways. Say we use satellite image, use UAV image, but they have the cone of low resolution. And so in Taiwan, what we do is we have drivers, we call them emulators. They drive a scooter in the field road, in country road, and take photos. And then they identify what crop it is. And the purpose of doing agricultural survey is to stabilize the product, the price of the crop products. Say if you have one crop that is, the amount is too large, then the price is going lower, and that's not happy by the farmer as well as by the government. So that's the purpose of doing this. But currently we are doing this very manually, in a sense that we can see there's an application, mobile application, developed by our Council of Agriculture. So the process is like that. We open this application, and then we identify, actually the GPS signal tells you where you are, and then you take a photo. So you can see like the photo on the right-hand side, those are sample photos. And then the emulators, they record what crop it is. And you can see this situation. So there's, the first big issue is those emulators, they are part-time jobs. So in a sense, they are not so professional. They are not well trained, and they can, leave anytime, and you have new emulators coming. So this crop identification is never easy and never accurate. And that is the problem we want to solve first. We want to identify one system that can identify AI system that can identify the crop automatically. And before doing that, we have to identify the non-crop image too. The emulators, they are paid by like the number of photos taken by the emulators. So sometimes, I'm not sure if they are doing on purpose, but they take photos, those are not crops like this. And say, this is called so-called out of distribution image. In the sense that you can see the figure on right, if those are, say the blue and green dots, those are crops, and we can know their distribution. If we know their distribution, and we know one image that is out of the distribution, we call it out of the distribution images, and we have to identify them too. Okay, so these are our objectives. You can see it's a little bit awkward that the two objectives are presented in a direction that is opposite from the introduction that I give, but I will let you know why later. So you can see first objective is to solve the OOD problem, and second is to identify 20 crops. And here are the 20 crops. You can see corn, rice, peanuts, yam, soybean, such as. So we have 20 total, and for each crops we collect say 600 or up to 2,500 images. And total we have more than 30,000 if I recall correctly. So we collect a lot of images. And say, so our solution is to create a system that can do this crop identification automatically. So that's to replace this very middle part, manual identification here. So our proposal is this. It includes 3 parts. The first part is the feature extractor, and second part is the OOD sample decoder, and third part is crop type classifier. And you may ask, why do I have to do it so complicated? Like you can use one CNN that if you feed image in, it can give you all the solutions. But regular CNN or the regular practice of using CNN cannot tell you the OOD image. You can see on the upper hand side, maybe I can use, oh, this is in Japanese that, so. On the upper hand side, you can see a gray bounding box. It's a manual identification. So still, we need to do something manually, though, to identify what the OOD image manually, because they can be buildings or they can be crops that is other than these 20 crops we are using, we are collecting. So still, but that's what we are doing this. Let me talk about the first part first, the vision transformer encoder, the feature extractor. So we use vision transformer as the encoder to encode the image, and to the input is image and output is some vector in high dimension space. And why do we use vision transformer encoder? Because it's the most accurate one in recent years. Actually, if I remember correctly, it started from last year, and it outperforms most of the CNN already. And we use transfer learning because transformer encoders are very big, so we have to do transfer learning, and that's the usual practice. And we have to fine-tune the transformer encoder using arc phase loss. And why do we use arc phase loss? On the left-hand side, you see a figure of some feature space that are trained by using the combination of softmax and cross entropy. So the issue of training using cross entropy is that the spreading of one crop can be very large. So like the boundary between the crops are very narrow. But if you use arc phase loss, you can see their distance is far, far away. And that's the property we need. So that's the very first part. The training process, such as I don't want to explain the details. And let's move to the second part, the OOD sample detector. And in the very first step, we have the vectors from the vision transformer encoder already. That's the red part one, feature vector. Now consider you have the feature in a very high dimension of feature space. That can be like 1,000 dimension. Now we want to identify if one image that is one vector in this feature space is an OOD. So how do we do that? There are several steps, but the main idea is that we want to calculate the distance between each class or each the centroid of each class and the image input V1 point over there. And to do that, we have to use the Mahalanobis distance because it considers the variance as well as the covariance between data. So that's the best choice. And for doing this part, we collect again a lot of data and split the data into training and tests at a ratio approximately 8:2. Okay. Now, in the training part, we have to first to model the distribution of the known samples. Say blue and green, they are known crop distributions. And we have to find their boundary. And we use the maximum likelihood estimation. And next, we calculate the distance between the centroid and the one input image. And then we use a threshold. Actually, we determine the threshold. So if the point is beyond the threshold, it is an OOD. And but it has to, beyond the threshold of all the crops. We have 20 crops, so we need to do this 20 times, 20 times actually. And here is the result. So remember, we split the data into training and tests at the ratio of A/2, right? So this is the test results, and we reach an accuracy of 97.99, and that's pretty high. And I think it's very useful. Now, is the last part. It's the crop type classifier. Okay, the classifier is pretty straightforward and easy. It's you can say it's a fully connected network or just a regular ANN, and we use a three-layer perceptron, and the perceptron is trained use closed entropy loss. That's the most regular, most common entropy loss that we are using. And again, the data is split into training and test. And here is the overall test accuracy. You can see the accuracy is 95.08. And here we come to conclusion, just a summary that for our OOD, the model is 97.99. And for the crop classification, the accuracy is 98.80. And I would like to acknowledge the partners that help us. So this is my presentation. Thank you very much.
Thank you very much. At first, my deepest sympathy with the youth student Lin-san.
Thank you.
Yeah. Okay. Do you have any questions and comments?
So quiet, no question at all. I'm more than happy to, yeah, please.
Okay, please use the microphone. Yeah.
Thank you very much. It's a very nice presentation.
I can't hear you.
Sorry. Thank you very much. So we have anomaly detection, usual way of detecting anomalies. And could you please explain what's the how OOD is? What are the differences between OOD and anomaly detection?
It's basically anomaly detection, but in a sense, we are dealing two problems together. One problem is that we have images that is not cropped at all. The other is we are dealing with the problem that the crop is not, the 20 crops that we have collected their images. So it's actually a anomaly detection, but we have to deal with these two together. And to do that, we identify its anomaly, and there's a manual process that will be further used to determine which one it is. It's not crop at all, or it's some other type of crops.
Thank you very much.
Thank you.
Any other questions? Do you have plan to apply this to the not the crop identification, not the cultivars difference?
What difference?
This time you just you apply this the crop difference, but
Right.
Variety difference.
Variety difference. Oh, yes, this can be done in a sense if you take a close-up image of crops. Yes, it can be done, but it's a totally different problem. And our first priority for now is to finish this project because since my student's gone, that I have to find another student who is willing to do this first. And variety difference is more like the phenotyping problem.
Yeah.
But certainly, if the difference is obvious enough, and if the image is close up enough, we can do that for sure. Thank you for the question.
Thank you very much. Okay, almost time. Thank you very much.
Thank you.
Okay. じゃあ、 Next presentation is by online. No? Yes. So, okay. じゃあ、じゃあそれよ。Shall we move on the next presentation? The title is